All right, here we go. So the last thing that I need you guys to write down, and just so you're aware, all I really care about is this part right here. So let me have you write this down. Substitute teacher, you can press enter to pause as they write this down, and then we'll pick back up. Now that we are ready to roll. Indirect measurement is when you use similar triangles to find measurements that would be difficult to find directly. The way this is used in real life are like these two examples that you see here. The first example deals with shadows. If you could imagine that the sun is over here somewhere. I don't know why my sun is blue, but that's what pen color I have. And the sun is casting rays, but you have to remember this sun is way out, million light years away, right? Like really far away. Hundreds of thousands of miles away. So by the time the light gets here, the light's going to hit the top of the tree and come down, and the light hitting the top of the man and coming down to the ground, creating the shadows, is going to create two shadows that have two angles that are the same. And so what we can do, since this person is standing up straight and down and that tree is going up straight and down, what we can do is we can figure out how tall a palm tree is without having to climb up and take a measuring stick to it or a tape measure. We can use proportions. It's easy to measure the guy who's 5 feet tall and the shadow 6.5 feet long. And how tall is the tree? We don't know, but we know that the shadow, because that's easy to measure the shadow since it's on the ground, we can figure out how tall palm trees are. That's one way. By the way, you could also have this guy stand right about here where they share the shadow, and that would be a very similar way to set up this problem to solve for it. We're not going to solve it, but I want you to see that you can figure out very tall objects by using shadows that have the same angles. And technically, once we know that by angle, that those two triangles are similar, then we can figure out that they're proportional and solve them. Here's a second way you can figure out how tall something is. There's a street light. You want to know how far it is off the ground. Or better yet, let's say you're driving something and it needs to go underneath a street light. I don't know if you've ever seen trucks hit street lights before, but that has happened because the bottom of the street light has to be a certain distance off the ground. Here's one other way you could do it. Some people put a mirror on the ground, and you can measure the person from their eyesight to the ground. If they can see the top of the stoplight in the mirror, then that must mean that this angle down here is the same as that angle there. If these two angles are the same, and this is at a right angle, this is a right angle, then that means these two triangles are similar. You could figure out how tall it is to the top of this stoplight if you knew this person's eyesight height. Let's say that person is 6 feet. And how far away is the mirror from the person's front of the toes there? And let's say that that's 4 feet. And then you can figure out how far it is directly below here to the mirror. And next thing you know, you have two triangles that are similar that you could solve. These two examples are not in your textbook. I found them on the internet, but I wanted you to see them because this is how it's used in real life. Sometimes people ask questions like, when am I ever going to use this in real life? Have you ever asked that question before? When am I ever going to use this in real life? Yes, I'm sure some of you may have heard somebody say it. Well, guess what? In real life, you need to figure out how tall you're going to go put something in that tree. I don't know what you're going to put in that tree. Maybe you want to decorate it for Christmas. You got to figure out how tall of a ladder you need. I don't know. You might need to figure out how to go underneath the bridge, and you're like, how tall is the bridge, or something along those lines. You could figure these things out using similar triangles. Now, with that being said, I have numbers 20, 23, and 24 are examples. So if you want to just go straight to your book and pull those out, you're welcome to do so. If they need time, feel free to press pause. Otherwise, I'm going to go right into it. Number 20. A 2-foot vertical post casts a 16-inch shadow at the same time a nearby cell phone tower casts a 120-foot shadow. How tall is the cell phone tower? Notice there's no picture. And it says indirect measurement. We're going to have to measure this indirectly. We have a post. And it's how tall? It's 2 feet tall. And it's vertical, so it's straight up in the ground. It has a 16-inch shadow. At the same time, that must mean that the shadow of the cell phone tower, they have these little things on them. Or if it's fancy, it's a fake tree, but there's our cell phone tower. And then there's going to be a shadow of the cell phone tower. And it has a 120-foot shadow, just like that. How tall is the cell phone tower? That's our X. So I have this little picture that I kind of drew here. And I wrote a little side note to you, so I want to make sure you see it. It says, pay attention to matching units when setting up proportions. The reason I say that is because if I'm looking at this shadow length and it's 120 feet, and this shadow length it's in inches, these don't match. Feet, inches, feet, and I'm pretty sure I'm going to measure this in feet too, over here. This is something that's not matching in the units that we started with. So I'm hoping that you're looking at this and going, oh, I'm going to need to convert it, because you are. I would convert this and say, how many feet is that in? And a decimal will be just fine. So let's see, there are 12 inches in a foot. There's 16 inches times how many inches in a foot. 1 foot is 12 inches. So I'm going to do 16 divided by 12. The inches will cancel, and I can see how many feet that is. I'm going to do that as a decimal. Doesn't come out pretty. Or a fraction. Fraction is even easier. Guess what that is? That is 4/3 feet, or 1.3 repeating. Okay, use my calculator for that right there. So now that we know that, we can set up our proportion. X over 120 feet will equal 2 feet over 4/3 feet. I'm going to do this as a fraction just because I feel like it'd be good for you guys to see it as a fraction. Okay, I went how tall over its shadow, how tall over its shadow. You can do it that way. Some of you might go shadow over shadow equals how tall over how tall. Guess what? Because they're proportions, you can do that as well. It's up to you. But what you do from here is you're going to multiply the diagonals. 4/3 x equals the product of the other one, 2 times 120. I'm getting 240 there. And 4/3 x. What I do after that is I multiply by its reciprocal, 3/4. 3/4. 4 goes into there 60 times. 4 goes into there 4, 6, 24, yeah. 60 times the 3 is 180 feet. How tall is the cell phone tower? 180 feet. There's my answer. I'm hoping that shows you exactly how tall, how we can figure those things out based off of something that we can measure very easily. Scooting to number 23. For each pair of similar triangles, find the value of x. So what I want you to see on this problem is, I wrote a little note on number 23. Pay attention to small triangles and big triangles when setting up proportions. So if I'm looking at this small triangle, we'll call it the blue triangle that I just colored in here. And I do the left side of the blue triangle over the bottom of the blue triangle. That's the small triangle. Then if I'm setting up my proportion, and I'm looking at the big triangle, I'll call this one the red triangle, as I colored it in red right there. I went left side over the bottom. I need the left side over the bottom. What's the left side over here? Of the red triangle, the left side, the big triangle. I'm hoping you see it's 20 and not 10. Don't just go, because there's a 10 and a 10. The mistakes that some students make is that they just look at that 10, but don't forget it's the whole left side and the whole bottom is 6x. I only say that because I've seen students make that as a simple mistake, and I want to prep you so that you're not making those simple mistakes. Now let's do the cross products. Product of the extremes, 6x times 10 is 60x. The product of the means, 12 times 20 is 240. Divide by 60. I believe it's 4. Did I answer the question? Find the value of x. Yes, I did. I always say that because I didn't know if they want me to, like I go, is 4, does that reasonable answer? 6 times 4 is 24. Oh yeah, that makes sense. Then it makes it a mid-segment. That'd be perfect for that. Last example. Your last example is number 24, which is a proof. Now for this example, what I would like for you to do is I'd like to see what you can come up with. Okay? This is number 24. Number 24, that's what's given. That's what you're supposed to prove. And I thought about just letting you go for it. And then I thought, here's what I'll do. I'll start you off. Here you go. Go ahead. Pause the video. When you're trying 24, see if you can fill in those other spots.